like 2 weeks to Florida State University. Thank you for the invitation. And today I'll talk about Dirac neutrinos and parity solution for the strong CP problem. Great. Here's the outline for my talk. I'll try to give a motivation on Dirac neutrinos. I'll give a lightning review on Majorana neutrino mass models and how we can test this kind of models, Majorana neutrino mass models, through electron flavor violation, just to give a background. And then I'll go and start to talk about Dirac neutrinos from left-right symmetric theory and how we can embed this kind of version of left-right symmetric theory into gut. Okay, in this one, I'll talk about parity solution to a strong CP problem. I'll also talk about Dirac neutrinos can be tested through an effective, and then gut embedding will predict deltaCP and light neutrino mass whenever you're trying to embed left-right symmetric theory into gut. And I will also see why it's so difficult to construct a model for Dirac neutrinos on light Majorana neutrino mass. Okay, then I'll finally conclude. Okay. I think I need to remove this. Okay. Okay, as you know, the strong CP problem, the QCT Lagrangian will violate the term. It allows the term that violates parity and time reversal. Through CPT, it also violates CP symmetry. So this theta bar term violates parity and time reversal. Okay, you can understand this by doing analogous to electrodynamics. Or if you have new term, you'll have this E squared minus B squared. E is parity odd and T even. B magnetic field is P even, T odd. And if you have F tilde, which is analogous to this dual, you have E dot B, which is both parity odd and time reversal odd. Okay, you can hope to remove this kind of term by chiral rotation. However, any chiral rotation you do in the quark field will just redefine this new parameter theta to be theta plus alpha, whatever this chiral rotation you do. So the only invariant physical quantity in this term is theta bar, so-called theta plus theta q, or theta plus argument determinant of mq, where mq is the mass of the quarks with multiple flavors. So in any theory, there is no reason for them to cancel, of course. So what is the consequences of this theta bar term? Of course, this theta bar term, moving forward, yeah. This theta bar term will induce neutron electric dipole moment. Okay, on one naive estimation of this neutron electric dipole moment is this formula. Forget about all the terms, but this dn is essentially 3 times to the minus 16 theta bar each centimeter. But the current bound on neutron EDM is 3 times to the minus 26, which immediately tells me that this theta bar term is less than 10 to the minus 10. Of course, the mass parameter can in principle have arbitrary phases, so this theta bar is expected to be order 1. But experiment, of course, tells you that theta bar is less than 10 minus 10. So the question is, why is this theta bar so small? This so-called strong CP problem. Okay, that's it. So we're trying to resolve that. So there are various solutions to the strong CP problem. The first one is, what if you consider massless of quark? Of course, spoiler alert, the quark mass are not 0. Okay, if you do that, you can do a chiral rotation to remove this theta term. Of course, and U equal to 0 is inconsistent with both experimental data as well as lattice calculation. The second solution is axions, very widely studied solution, and probably is quite beautiful, of course. What you do here is you make this theta bar term a dynamical field. So you have global U1 symmetry, and you break it spontaneously, then you have Goldstone modes. Okay, to QCD, this Goldstone mode will get mass, and so we call it axions. Okay, once you have these axions, you can write this interaction term like this, and then basically this effective potential will relax so that the vacuum solution will relax to theta bar to 0. Okay, this is an elegant solution to the strong CP problem. The other solution is to make this parity or CP symmetry to be exact, and you spontaneously break it. Okay, so you make this P or CP to be exact symmetry, and you spontaneously break it such that the determinant of the quark mass matrix is real. Again, remember that this theta bar is theta plus argument determinant of MQ. So if you have any theory which to begin with, it is parity symmetric, for example. So this theta first term is already 0. And if you make MQ mass of quark mass matrix is real, then you solve a strong CP problem. And this is the solution I will be talking about. Unlike most of the people who talk about axions, and I'll talk about this more on this later. Okay. The second shortcomings of the standard model is, of course, neutrino mass. Okay, which we all love. Okay, neutrino mass, of course, are predicted to be zero as standard model. It oscillates. You can imagine this oscillation through a flavor of neutrino produced at the neutrino source. It oscillates and it is detected, or different flavor of neutrino is detected at detector. This probability from one oscillation going to a different flavor, one flavor going to a different flavor is given by this simple formula. Or this U is UPM, unitary matrix, which will give you the transition from a flavor eigenstate to a mass eigenstate. Provided that if neutrino mass are all zero, or if the neutrino mass are all same, the probability of from one flavor going to a different flavor will be either 0 or 1, which of course is not true from experiments. We know this probability is not 0, that means neutrino must have a mass and must be different. Okay, simply because of this. And this U is determined by these three different angles, theta 1, 2, theta 2, 3, and theta 1, 3, which are somewhat precisely measured, and delta CP, which we do not know. And there are different experiments, of course, to measure these angles. Okay. Within neutrino mass, we know that neutrino mass are not 0. Within neutrino mass, there are various open questions. First, we do not know octant of theta 2, 3. If I go back here, theta 2, 3 it can be anywhere from 39 to 52. So we do not know whether it is below 45 or above 45. We want to understand which octant it leaves. Okay. The second is absolute mass scale and mass hierarchy. We do not know absolute mass scale of a neutrino, as you can see from this plot. And we also do not know whether the nu 3 is the heaviest state or nu 2 is the heaviest state. So it's so-called normal hierarchy or inverted hierarchy. Okay, we're trying to understand that. We're also trying to understand whether the neutrinos are its own antiparticle, whether they are Dirac fermions or Majorana fermions. Okay, and we also are trying to understand if there's CP violation in the left-hand sector is deltaCP. And also, of course, from a theoretical point of view, why is neutrino mass so tiny? So you can see from this, the neutrino mass is at least 6 or 7 or smaller than electron mass. So from theoretical point of view, we're trying to understand why the neutrino mass is so tiny. Also, as I told you, the non-zero neutrino mass necessarily mean that you have to have existence of new fundamental fields. So we have to understand, so what are these new fundamental fields? Whether they're scalar, fermions, what are the spins of this particle, and so on and so forth. Okay, these are the open questions, which I'll try to address some of these in my talk. Okay, again, going for the neutrino, Dirac versus Majorana. For you to have Dirac neutrinos, by definition, you need to have a right-handed neutrino, a NUR. So you introduce the right-handed neutrino, which is not in the standard model, of course. So we just simulate under the standard model gauge group SU3 color, SU2 left, and U1 hypercharged. And you can write a term like this, Y nu L bar, which is a electron doublet, H is the Higgs doublet, nu R is a new field that you add. Okay? And if neutrino is a Dirac particle, so if you somehow forbid this nu R in your term, then you can, after spontaneous breaking of symmetry, H gets the vacuum express value, and the neutrino gets the mass like this. So if the neutrinos are Dirac particles, U1L is conserved. Okay? But however, we know that neutrino mass is very, very tiny, 0.1 electron volt, which also means that Yukawa coupling associated with this interaction term is extremely small. So what does it mean? It means that no matter how many Higgs you produce in LSC, for example, billions of Higgs, you will never be able to probe this tiny Yukawa coupling. Simply because there are no other interaction for the neutrinos usually in the theory. Well, Dirac neutrino is fine, it's very simple, but there is no way to probe it, at least in the current LSC. But the alternate option, of course, what if the neutrinos are Majorana particles, where the electron number is explicitly broken? Okay, one of the tests for this electron number breaking is, of course, neutrinoless double beta decay, shown by this diagram, where you don't have neutrinos, but you just have 2 electrons in the final state. And this kind of Majorana neutrinos can be generated through Weinberg operator LLHH. I'll just give a brief introduction to that as well. And I'll talk about Majorana neutrinos, and then I'll talk about Dirac neutrinos. You'll see why getting a Dirac neutrinos from model perspective is so hard, okay, compared to the Majorana neutrinos. So here's the recipe for neutrino masses. How do you generate neutrino mass? What you do is, if neutrino is Majorana, So the lowest non-renormalizable standard model effective operator is the Weinberg operator, which is LLHH. L is electron doublet, H is the Higgs doublet. This Y is dimensionless coupling, lambda is some new phase scale. Okay, in the simplest form, after spontaneous symmetry breaking, when H gets the critical value, the neutrino mass is given by this. Y times V square over lambda. V is again of our 100 GeV, to be precise, 246. Okay, and then if Yukawa is order 1, and then the neutrino mass is 0.1 electron volt, that implies that this new scale is in the 14 GeV. So in the simplest form, of course, there are of course tweaks you can do. In the simplest form, the seesaw scale is very, very high. So the testability is very low. Okay. Of course, you can rewrite this Weinberg operator as generalized Weinberg operator with just adding H range. So why the advantage of going to a higher dimensional operator? Because higher the dimension, the lower the new phase scale you can have. Okay. This is the operator you can write to generate neutrino mass and break the electron number by 2 units and get the neutrino mass. So what is the next step? Once you write the operator, you open up such operators, which means that in other words you be completed. Okay. So how do you do UV completed? You draw this kind of diagram, dimension 5, dimension 7, dimension 9, and you try to UV complete it. Okay. So what are the new particles so that you can generate this kind of operators? Let's take one example. LLHH. Okay, it's much simpler than you think. Okay, to build up a model for motion and neutrino. So let's say you have this LLHH. Again, L is a electron doublet, H is a Higgs doublet. This is a Weinberg operator. I know this is an effective operator of dimension 5. Okay, what you do is you draw the topologies at 3 levels, at 1 loop level, at 2 loop level. At key level, you can see there are 2 different topologies. First topology is this one, the second one is this one. Different topologies. Okay. Once you draw a topology, you write the quantum numbers for L and H. Of course, you know the quantum number for L, which is electron doublet, 1 to 1/2, negative 1/2, H is 1 to 1/2. Once you write this quantum number, then you try to see which is the new particle that is a gauge singlet. Okay, there are 2 options. Either one is a singlet or a triplet. And these are fermions, of course. These solid lines are fermions, gas lines are scalar fields. Okay, and if you have a singlet, of course you have to also make sure that it is Lorentz invariant. But if it's a singlet, it's called type 1, very widely studied. If it's a triplet fermion, is a type 3. If it's a triplet scalar, it's called type 3. Okay, this is what so-called type 1, type 2, and type 3 seesaw mechanism. Of course, this is at 3 level. You can go to loop level as well. Okay, where you have LLHH, you can draw like this kind of topology. There are other topologies, of course, and these are second topology. And if you know something about relative neutrino mass model, this is popularly so-called sportogenic Ma model. Okay, this is so-called Z model. Again, each of them have a name. Okay, but which is again widely studied. I'll give one example. And this is again you can draw a single topology at 2 loop level. This is so-called Z-Babu model. Okay, it's again 2 loop model, but different ways to generate neutrino mass. All you're doing the exactly same thing. You draw and you put all the quantum numbers. These are gauge singlet, make a gauge singlet, and make sure. Okay, then you get neutrino mass by making the electron number. Good. So the other question is, how do you test such kind of models? Okay, hold on. I'm going to talk about Dirac neutrinos just in a second. Okay, I'm just giving you like a brief lightning review on mass around neutrino mass. So of course we know that there's a flavor transition in the neutrino mass. So the neutrino has a mass. So it proves that flavor transition. It proves that it's kind of a global symmetry. Le, L mu, and L tau is broken. Okay, it's broken. So electron flavor is definitely violated, because we know that one flavor goes to a different flavor. So the question is, where is it? Okay, so this is one way to test this kind of models is through different flavor violation. So if you have Dirac neutrinos, just this term, right? Dirac neutrino is just, you just add right in a neutrino and you just have this term. That means the Yukawa coupling is quite small. Okay, and assume that the newer is forbidden by some additional symmetry. So if you just have this, the electron flavor violating amplitude is proportional to m nu, neutrino mass over mw squared, which is R of 10 to the minus 24. So if you do calculate the actual transition, it will be absolute, again, square of this one, 10 to the minus 48. So there is no way you can probe this tiny amplitude in experiment. So there is no way to probe Dirac Newton through lepton Flavor violation. Well, so what if it is modular neutrino? Let's take a seesaw case. Neutrino mass is induced by Weinberg dimension 5 operator. And you can write again, you add that in a neutrino, but you write this MR, new R term, the modular mass term. So this is again one of the topology that I mentioned before. It's just reverse. Okay, LLHH is a diagram. Once you do this one, the neutrino mass again is proportional to MD squared, which is the Dirac mass term, which is MD over MR, which is the new physics scale that you introduced. And the amplitude in this case as well, it is for the lepton Flavor violation of mu TEM, for example, is proportional to M nu over MR. It's again suppressed. However, you can always play with the structure of MD to give a large effect. For example, this is just an example. Okay, when you deviate from seesaw framework. Well, what is a seesaw? Seesaw is you bring a new physics scale, and this new physics scale will suppress the neutrino mass. But if you have some kind of unique structure on MD and MR, then there is no seesaw anymore. You can arbitrarily make A, B, and C whatever you like, and mu to be whatever you like, and you still get a neutrino mass to be correct, and you will get a very large prediction for the lepton Flavor violation. Okay, and there are many different structures like this where you deviate from seesaw framework. Okay, this is how we do for type 1 and type 3. What about type 2? Type 2, again, you introduce a scalar field, right? This is another topology for generating neutrino mass at tree level for dimension 5. Okay, once you have this one, this neutrino mass is proportional to Y, which is the Yukawa coupling. Okay, times this delta is the vacuum expectation value or induced vacuum expectation value of this three-plate field. Okay, as you can see, this neutrino mass directly proportional to the Yukawa structure. Remember that to get neutrino mass, the flavor is somewhat fixed. Okay, the 3x3 matrix is somewhat fixed. The Yukawa coupling also now is fixed. Even the individual lepton Flavor violation is small, but the ratio of the lepton Flavor violating processes is kind of uniquely predicted. Okay, which was shown by this group. So there's a prediction on lepton Flavor violation through the neutrino mass structure itself. Okay, what about relative models? One example is the model where we have LLHH. Okay, now instead of having a tree level, you induce the neutrino mass at group level. Again, the same game. You're just adding new particles and so on, and then trying to generate neutrino mass. So what are the advantages? Of course, every loop you have a 16 pi square separation. So you're trying to explain somewhat naturally how you generate neutrino mass. Okay, in this Z model, okay, this is exactly a topology, this topology, nothing more. Okay, so what you do here, you add a singlet, charge singlet, and a doublet, second doublet to generate neutrino mass. There is no fermions at all. So once you add these two particles, there is no tree level term. Just by choosing the right new particles, there is no tree level term. The only term that you have is at loop level, which is shown as this diagram. Again, this H2 is a doublet, the second doublet, and eta plus is a singlet, a charge singlet. Once you have this one, this eta plus, H2 plus, and H1, this term will violate the number by 2 units, and then you generate a neutrino mass. Very simple as that. Okay, and the neutrino mass can be written like this, where kappa is some one loop factor, one loop function. Okay, F is a Yukawa coupling associated with eta plus. Y is the Yukawa coupling associated with H2 plus. Okay, there are two different Yukawa couplings. So that's the, again, do you have a prediction? The prediction goes, it is quite difficult to have a prediction because you are introducing new and more new parameters. Okay, the neutrino mass is 0 at tree level, right? And you remember this, right? And there is no right hand neutrino. It involves two scalars that breaks the lepton Flavor violation, thus you have a neutrino mass, modular neutrino mass. Smallness of neutrino mass is explained by this loop factor, 1 by 16 pi square at least, somewhat suppressed. And chiral suppression, if you look at this formula, this neutrino mass is proportional to the charge lepton mass. Okay, it is directly proportional to the charge lepton mass. So you have somewhat understanding of why neutrino mass is so small. Okay, and the new field scale in this kind of framework may lie at TV scale if it's connected to some, let's say, G-2. It can be connected to something else, but if it's connected to G-2, it has some prediction of lepton flavor violation shown by this plot. Okay, so here this is branching ratio to mu T gamma. This is a branching ratio to tau tri-lepton decay or tau lepton decay. Okay, and all these gray shaded regions are excluded. This red and pink can be probed, but this blue and green cannot be probed through lepton flavor violation. However, if you look at this, whenever we did the scan, whenever we look at this kind of data points, it turns out it follows this texture zero structure. And this texture zero has some unique prediction either in the double beta, this M beta beta, or the sum of neutrino masses, whether it's normal or inverted hierarchy. So somewhat you have somewhat control on how to test this model, for example, to lepton flavor violation. Good. Enough about Majorana mass. The question is, of course, what if neutrinos are Dirac? Okay, whatever I just talked about, well, it's not available anymore. Of course, neutrino may well be Dirac particles. It may just like electrons. Okay, the delta L lepton number is conserved. Okay, oscillation experiments cannot distinguish whether neutrinos are Dirac or Majorana. If it's Dirac neutrinos, really, so which is important to understand the smallness of their mass. Why is the neutron mass so small again from theoretical perspective? So one of the attractive features of Dirac neutrino is you can also have Dirac leptogenesis to explain baryon atomicity, matter-antimatter asymmetry. Okay, it's an attractive feature done by this Dick and Linder in 1990. And Dirac seesaw can be achieved through mirror models. Mirror models exactly have like a mirror copy of standard model. Okay, so one other way to generate Dirac neutrino is through left-right symmetric theory, which I am going to talk about. Okay, remember that unlike Majorana neutrino, so to have Dirac neutrinos, you do require right-handed neutrino. If you just add right-handed neutrino to the theory, this nu R term, right-handed neutrino, you can write nu R Majorana term. It automatically becomes a Majorana neutrino. So you have to have extra additional symmetry to permit nu R term. But unlike, so there are not many. There is one very good model, mirror models. The other one is left-right symmetric theory, where you can naturally have Dirac neutrinos. Okay, good. Let's talk about left-right symmetric theory. And I also talk about how you can embed this left-right into gut. Right. So Dirac neutrinos from left-right symmetric theory. Okay, gauge symmetry in the left-right, from the definition, of course, is extended to SU to left is extended SU to right across U1x. Okay, you have gauge symmetry is extended. The fermion is this QL is the quad doublet, LL is the lepton doublet. You have QR and LR. So by definition, all the fermions are a part of a multiplet. You can see right-handed neutron is already a part of gauge multiplet. Okay, fermion multiplet. It's already there. Okay, of course, now I have to make sure that you are not breaking the lepton number at any point. Otherwise, you'll have Majorana neutrino. You will not have Dirac neutrinos. The Higgs sector in this framework is quite simple. You just have two doublets, HL and HR. By definition, if you're left-handed, you should have right-handed because it's a left-right symmetric theory. Okay, you have HL and HR, unlike the standard left-right Higgs field. Where in the standard left-right, which have been widely studied, we have bi-doublet field and delta L and delta R, two triplets. So it is quite extended. Here you just have two doublets. Okay, and then the left-right symmetric theory to the documentary value of HR naught is broken to the standard model gauge symmetry. HL will break the standard model gauge symmetry to U1, usually U1. Okay, and the parity is of course exponentially broken, which is a left-right theory. And now we can ask, well, if you have these two doublets, how do you generate fermion masses? Okay, in this left-right theory, the phi to 2, you can write QL bar phi QR term, LL bar phi LR term. Here, since it's a doublet, you cannot write like that term. Okay, so you pay the price. You have a simpler Higgs sector, okay, but you have to pay the price of introducing vector-like fermions. Okay, so you have to introduce vector-like fermion to realize fermion masses. It turns out once you add this U type, it's a D type vector-like fermion. E is charged lepton. It's a charged lepton type vector-like fermion. Okay, once you add, you have mass for the charged fermion like this. Okay. Now instead of having seesaw framework for the neutrino, we have a seesaw framework for the fermion masses. So you have somewhat understanding why the fermion masses are different. But because now it's a seesaw, it is controlled by this vector-like fermion masses. M. Okay, so the seesaw fermion, seesaw for the charged fermion. Remember, there is no neutral vector-like fermion. So since there is no neutral vector-like fermion, you don't have a neutrino mass. Okay, right now until this point, there is no mass for the neutrinos, and I will tell you why I'm not adding one more particle just to get neutrino mass at tree level. Okay, but it turns out in this theory, WR and WR is absent at tree level, but WR and WR can mix at one loop level, which in turn will induce two loop Dirac neutrino mass. Oh, it looks complicated, but higher the loop, as a theorist, I'm happy. Higher the loop, you have more suppression. Okay, this is a two loop, you have a two loop. So at two loop, you have going to nu R, this is a vector-like fermion, and you generate a neutrino mass at two loop order. So flavor structure of this need to be studied to check the consistency of the neutrino oscillation data. So in this kind of framework, you have neutrino mass at two loop order. Good. So we did that. Okay, so this is just oscillation fit. So it turns out that it has enough parameter to fit oscillation data. Both normal and ordering are allowed. Dirac CP can be anything you want. No need to miss the decay. Electricity is not really constrained. If you want to understand why it's not constrained, I can tell you more detail because you have two diagrams. One is longitudinal mode and one transfer mode. So the one in the longitudinal mode plays a role. That's why there is a no scale for the electricity breaking. Good. Well, this is all nice, but this is not enough. This concrete prediction. Okay. So universal reflexivity theory, this theory can also solve the strong CP problem. I'll tell you why. Whenever I try to embed that, it's the exact same procedure. Okay, how to solve strong CP problem without axions. Okay, the model can be tested to an effective. Let's talk about an effective now. So CMB, cosmic microwave background, is sensitive to any extra radiation density. Okay, so of course nu R is ultra light new degrees of freedom. So which also means that it contributes to radiation density of the universe. So this kind of is parameterized by an effective, okay, and it's measured in units of extra neutrino degrees of freedom. Dirac neutrinos of this kind of model will modify an effective by 0.14, okay, which can be, you can look at it from this plot. Okay, in the standard model, an effective is 3. Okay, so this n effective can be improved by CMB stage 4. I don't know what is the status of CMB stage 4. Okay, different story, but it can be proved. Okay, so it is valid if you have 3 right-handed neutrino. It changes the n effective. It is valid if the 3 right-handed neutrinos are in thermal equilibrium with the standard model plasma in the universe. If they are not in thermal equilibrium, then it's not valid, of course. So this gives a strong constraint on this left-right model, this kind of left-right model, or any Dirac neutrino mass model of this type. Okay, so this is the prediction, of course. So you can see this is a decoupling temperature of right-handed neutrino. This is an effective, delta N effective. So no matter where you decouple the right-handed neutrino, whether you decouple at the weak scale or all the way to the cut scale, you can still predict the N effective to be 0.14. Okay, this basically tells you that whether it's 3 right-handed neutrino or in thermal equilibrium with standard plasma in the universe. That's all it will tell you. Moreover, this Planck plus BO, the current down, will also put a lower limit on WR mass in the left-right theory, of course. Because this right-handed neutrino is directly proportional to the WR. It turns out it has a lower limit of 70 eV at WR mass, which is better than LSC, for example. LSC are 340 eV. Okay, good. Okay, this is a Dirac neutrino, a very nice model for Dirac neutrinos to left-right model. Okay. What I want to do is ask the following questions.
So yes. You introduced the vector-like quartz.
Yes. Yes. I introduced vector-like quartz. So now if you know something about that, okay, it is going to be challenging. Yes.
So you also got like a hierarchy in the web of the HR and HL.
Yes.
So how do you do you just put it by hand or is there something?
Yeah. I mean, so in this kind of theory, here. here. You have to break this HR, definitely breaks the left-right symmetry. Okay, so this HR they call it VR. Okay, this is really proportional to the gauge boson masses. The gauge boson mass is constrained to LHC, for example. This is 14, and they already put a very good limit on this breaking scale to be around 10 TeV. It has to be at least 10 TeV. Okay, from phenomenology, you have to make sure that you put it by hand. Okay, you guess the sort of then you put access at 10 TeV, and then you break this HR is again you to give it to 46 TeV.
But I can't like but I have like do it naturally in the model and you going to use something else, or I just like tune the parameters, just like change my values.
You just need to introduce a scale at whatever scale you want to do. Okay, of course, in this theory, as I was telling you, WR mass is not constrained. So it can be anywhere from 10 TeV, again, phenomenology because of 10 TeV, all the way to the gut scale. Okay. Okay. Now I want you to ask the following questions. So here, good. I know this left right is very good to solve strong CP problem, which I'll tell you later how. I know this left right symmetry model will have Dirac neutrinos. Okay, but I also know that it has no prediction at all. Okay, normal hierarchy is allowed, both invariant is allowed, deltaCP is not constrained, and so on and so forth. So I wanted to ask you this question. So can we embed this? We know that standard left right can be made into gut, SO10, for example. Okay, can we embed this kind of left right version into gut theory while preserving the Dirac nature of neutrinos? I want to have Dirac neutrinos. Okay, I'm thinking that this neutrino is technically Dirac particle. Is there any prediction in neutrino oscillation? Whether can I predict whether this is normal or inverted for the neutrino, or whether it is a Dirac, whether if there is any prediction in Dirac CP? And can we still solve the strong CP problem when we try to embed into that? And of course, I can always ask the theorist, what else can the model do? Okay, yeah. Good. So turns out this kind of model has a natural embedding into SU5 left plus SU5 right. Okay. So the fermion spectrum of the model has natural embedding SU5 left plus SU5 right unification. All left-handed and right-handed fermions of the standard model fit into 10 plus 5 bar of SU5 left and SU5 right. Okay. The remaining vector-like quarks and leptons, as you asked, you have three of them: up-type quark, down-type quark, and charge-type quark. So charge-type vector-like fermions. Okay, that naturally fit into this 10 plus 5 bar. This is 5 bar, of course, fundamental representation, and this is a 10 representation. You can see these are three different quarks for down type colors. Okay, and this is again charged lepton. This is U type, is up type vector-like fermion. This again Q is standard model like Q left and Q right for the standard model, and this is E is a new vector-like fermion. Good. So it exactly fit into this 10 plus 5 bar. Okay, of course, why I do not have this neutral lepton to generate neutron mass? Because it does not fit into 10 plus 5 bar. For me to embed into that kind of theory. So of course, parity can be imposed at gut scale, of course, where psi L goes to psi right, because parity symmetry, left-handed goes to right-handed, okay, and chi L goes to right. Okay, good. Now, in any gut, this is very nice, but then you have to do all other. You have to make it handy. Okay, to make everything work right. So with standard model particles, okay, we obtain the following beta function coefficient and with properly normalized gauge coupling. B1 is associated with U1 as a charge, B2 is again SU2, and B3 is color. Okay, as you can see, it is 41 by 26. If you know anything about SU5, it's quite different from SU5. Okay, so what it means, what it implies, if SU5 and S5 cross SU5 is directly broken to the standard model gauge group, where GI is the gauge coupling made as a single value, you have this relation where alpha 1 normalizes 13 by 3, which immediately implies, forget about how I got it here, there, but which immediately implies sine square theta W at gut scale is 3 by 16, very small. Okay, what it means is if sine square theta W at gut scale is 3 by 16, now once you start to run the Weinberg angle from gut scale to the quick scale, it will become smaller and smaller and smaller. So there is no way you can reconcile this with the measure value at the quick scale. And this is some simple formula F sine square theta W at top quark mass. You are not going to get it right. What does it imply now? Which immediately implies that you cannot break this SU5 plus SU5 directly to the standard model. So you need to have some intermediate scale breaking, okay? So that you change the behavior. Good. So to break the SU5 plus SU5, like any gut, you need a lot of particles, okay? To spontaneously break to A1, you choose the following X multiplier. First, you have 75, 175 is a real representation, okay? Now you can ask, well, why not 24, 124? Of course, 24, 124 also can break. Okay, SU5 plus SU5, which is smaller representation than S75, 175. However, introducing 24, 124 allows this kind of terms in the Lagrangian. That will spoil the strong CP problem. Remember that my job is to also solve strong CP problem in that. Okay, then you need HL and HR. Of course, if you have HL, you need to have HR because of parity. Okay, and then phi is the bifundamental of SU5. It is required to have fermion mass generation. Okay, these three, 75, 5 bar, 115 bar, and 5 bar is required for the symmetry breaking. Okay, you have to break the SU5 plus SU5 to intermediate scale breaking, and then from intermediate you break this standard model. Okay, and also it turns out that you also require this 15 bar 15 just to get the gauge coupling unification. Remember that you have the weird looking guy here, and we have the sin square theta W is not coming out right. Just to make this come out right, you need this 15 bar 15. Of course, you can ask, why not 10 bar 10? It does do gauge coupling unification, but it turns out whenever you add this 10 bar 10 bar, I'll tell you later why, but it allows rapid proton decay, which is not good again. Okay, because you are doing a gut, you'll have proton decay. If you have rapid proton decay, the case is consistent, of course. And of course, it also spoils strong CP problem. It also makes one of the gauge coupling Z5 right is the gauge coupling associated with SU5 right, non-perturbative. So that's why you choose this a minimal set of Higgs multiplets that can solve strong CP problem. That can everything is consistent, nothing is becoming non-perturbative. And also, you will get gauge coupling.
75 also make the gauge coupling to blow up because so many Higgs is there.
Gauge coupling, yeah, very good question. So I can address it later, but yeah. So you're right. So if you have below SU5 right, cross SU5 right, everything is fine. Now we can ask what happens above SU5 right and cross SU5 right. Since you have a very large multiplet, will not that the whatever gauge coupling that is getting unified at SU5 plus SU5, wouldn't that be non-perturbative? It turns out it is somewhat okay. So again, what is non-perturbative? If you allow it to be square root of 4 pi, it is fine. It is. But very good question, of course. Had I had this, these are scalar field. If I have fermion field, then it will definitely grow before reaching the Planck scale. So here is the symmetry breaking. SU5 right left cross SU5 right is broken by this 75, 175. Remember, it can also be 24, but then I don't want to use 24 because I want to solve strong CP. I'll tell you why again later. This is broken to 3, 2, 1 SU5 right. Okay. It is broken not is SU5 cross SU5 right, left hand side is broken, but SU5 right remains intact on the intermediate scale. Now you have to immediately ask, well, if SU5 right survives at intermediate scale, will not there be proton decay? Mitigated by the gauge boson of SU5 right. The answer is no, turns out. Okay, in this theory. Precisely because I'm not introducing this 10 bar 10. Good. And now then if I and HR break this to the standard model and then HR breaks the standard model to 0.1. The gauge coupling unification can be written by this RGE, renormalized equations. But this first term is one loop factor, one loop contribution, and this second term is two loop. As you can see, the two loop also have contribution of Yukawa couplings. The sin square theta W now, since you have intermediate scale breaking, without intermediate scale breaking, you just have this first term, which becomes smaller and smaller. With intermediate scale breaking, you are adding an additional term, which is 39 comes from this prime by 15, essential for unification. Once you have all this, you have a gauge coupling unification, where this is an intermediate scale breaking, which happens at 9 times 10 over 10. Okay, this is one of the solution. With alpha 1, alpha 2, and alpha 3 are the gauge coupling associated with the standard model gauge group. And above intermediate scale, you have alpha 1 left. Okay, alpha 2 left is SU2 left, alpha 3 color left is SU3 color left, alpha 5 right is this one. Okay, after this one, SU5 again breaks it breaks into SU3 color right, and then they merge is a diagonal subgroup, and then it becomes SU3. The SU3 is a linear combination of SU3 left and SU3 right. Okay. It turns out that the gut scale is 10^17 and the alpha gut is 13.18. Now you're asking, whenever I run this coupling above, will it not blow up before it's in the Planck scale? It does not. Okay, because 175 is of course bigger representation, it's a real representation, it is not that bad.
So the simplification so good, like, did you check it also in 2 loops? Like,
Yeah, I did with 2 loops. I did with 2 loops. Yeah, 1 loop is I did better result with 2 loops. Yeah, even I tried with 3 loops, but why to make life so complicated? I had done some 3 loop estimation as well. Good. Now, of course, how to design a fermion mass? So this is the Yukawa coupling at that scale. Okay, remember that I want to have some prediction as well whenever I try to embed. There are 3 Yukawa couplings, YU, YL, and YD. Now I have to fit all the fermion masses with these 3 Yukawa couplings. So here MU is given like this, ML is again up-type quad. It's a 6x6 matrix, 3 of them is like quad, 3 of them is better like fermions. Okay, this ML is again a 6x6 matrix, and D is down type. Okay, now here this is 0. This is very crucial for the proton decay. Okay, because of this 0, there is no mixing between vector-like fermions and normal quarks. If there is no mixing between those, there is no proton decay. Okay, and it's mediated by H5, right? Yes, boson. But it turns out the small Dirac neutrino mass are induced naturally at 3 level. Okay, I remember that in the left right I have 2 loops. Now 2 loops goes away, but it can naturally you can generate Dirac neutrinos by at 3 level by so-called type 2 Dirac. It's exactly like type 2 seesaw. Okay. However, this is more predictive because this Yukawa coupling you can parameterize like M intermediate or M gut. Because M intermediate and M gut are fixed from this coupling unification. And that uniquely will give you 10⁻⁷. So you have somewhat natural understanding why Dirac neutrinos are so small, basically. Okay. Here's the prediction for neutrino oscillation. So this is all the technical stuff, but this is MU, ML, and MD. You can see the MU is again 6x6 matrix. This MU is kappa R is the intermediate scale breaking, kappa I is the equal weak. Okay, as you can see, as soon as you fit this matrix into up-type quark, the vector-like fermion of up-type vector-like fermion mass are also immediately fixed. Because it is simply proportional to the up-type quark masses. Okay. And similarly to this one, but turns out all of these has one parameter to fit MD, the 3 light down quark masses. So it predicts there's 2 predictions, deltaCP and light neutron mass, which is shown by this plot. deltaCP is predicted to be under 30 or 229, under 30 plus minus. Okay, light neutron mass is predicted to be 4.8 to 1.
You are using a parity symmetry because to predict this delta.
Yeah, parity symmetry. These are all Hermitian power couplings.
Then you got this very.
This is uniquely predicted. Yeah. And you can see everything is correlated, right? I mean, and this MU, you try to put MU to the upward type quarks, and then ML, you put it as a diagonal matrix, okay? ML to the charge left, and as soon as you fix this one, ML goes here, and there's no more freedom anymore. So there's only one parameter, free parameter, the truly free parameter, and then you predict two of them.
And your so everything is real because that's it.
Yeah, it's very good question. So because that is very important whether we can solve strong CP or not. Okay. Yeah, I will address that. Proton decay. I'm running out of time. So Gauss boson again S5 right with intermediate scale, because S5 right is at intermediate scale will not lead to proton decay because of this 0-0 structure. There's no vector liking of the normal quark mixing. So you can have a diagram like this, but you cannot, there's no mixing with normally. And there is no mixing with E with normally, or the charge electron. So there is no proton decay. Of course, S5 left can lead to proton decay, which is at the gut scale. But since the gut scale is so high, the prediction for the proton decay is the lifetime is very, very large. So there's no way to prove this, unfortunately. Do proton decay at least. Okay. Okay, how do I solve the strong CP? One of the titles of my talk. Okay. Theta bar is theta plus argument determinant of MQ. Okay, let's start from there. Theta, of course, is coming from G dual, which is exactly like E dot B, right? With the color. Okay, so theta is parity or under parity symmetry. So therefore, any parity symmetry theory to begin with will have this first term go to values. Okay, it goes to 0 because you are starting with the parity symmetry theory. Okay, now of course this MQ is quark mass matrix. It is proportional to the parity between waves. And if we make sure that the argument determinant of MQ is real, so that this term goes to 0, then I solve the strong CP problem. Simple as that. But not quite. Okay. Of course, this MQ is the upward mass and downward mass. Again, this is a 6x6 matrix. Since you have like this, you can see the determinant of this matrix is just YU times YU dagger. Yes. So YU times YU dagger is a Hermitian matrix. Determinant of Hermitian matrix is real. I do exactly the same thing with here. Okay. So I prove, at least at this stage, that if you have S5 cross S5 parity, well, this Yukawa couplings are Hermitian, of course. Okay. Sorry. Then I prove that the theta bar is 0 at 3 level. Of course, as you are asking, what are the waves, right? If kappa L and kappa R, which are the waves, if they are not real, I don't solve again. So I have to make sure this kappa L and kappa R are also real. How do I make sure that? I choose the Higgs parameter in such a way that all of the terms in the Higgs potential are real. So if all the terms in the Higgs potential are real, it will admit solution where the waves are real. So
That's your assumption.
No, that's not my assumption. As soon as I choose this Higgs field, there is no term that has complex parameters. So if you have 24, for example, then you allow the term to write a term which has a complex parameter. If you have a complex parameter, then waves are not real. If all the parameters are real, by definition of by choosing the parameters properly, then all the waves are real as well. Okay, this I solve. Now I can ask, well, 3 level is good. Yeah. I don't have any symmetry to say that theta bar is 0. If 3 level is whatever 1 loop level or 2 loop level and so on and so forth. Turns out that quantum correction would, of course, it will lead to theta bar non-zero, but it may be below theta bar minus 10. Okay, arising from neutron medium. So it turns out that in this theory, the theta bar at 1 loop is also 0. For you to calculate theta bar at 1 loop, you have to discontinue to work in flavor basis. This is again technical stuff. Okay, then you can write this kind of propagator in the flavor basis like this. Once you do that, you can write loop corrected quark mass matrix. Again, theta plus the argument determinant MQ. The MQ is MQ naught, which is a 3 level term. Delta M is a loop level term. Can come from 1 loop, 2 loop, and so on. Delta MQ is 2 by 2 matrix. Delta M LL, LH. L is light sector, H is heavy sector. What does it really mean? This delta MLL is like down quark going to a right-handed going to a left-handed. It's a type of an example. And this again, right-handed going to a heavy quark. Okay, this kind of diagrams comes from this one. Once you have these things, once you evaluate this kind of diagram, you feed into this formula here. Of course, you don't have to really calculate, you have to just look at the flavor structure. Once you do that and you calculate theta bar, if it goes to 0, well, we solve the strong CP problem at 1 loop. And it turns out this is not just 2 diagrams, there are many diagrams. Okay, these are again down type, down going to down, or down going to vector like for down type 4, this is up type. So each diagram turns out gives exactly 0 contribution to theta bar. So I solve theta bar at 1 loop order. Okay, at 3 level, 1 loop order. Now we can ask whatever 2 loop order. Not so easy now. With a 2 loop, there are many diagrams and not so easy to calculate. But turns out I at least found one diagram where theta bar is not 0. Okay, and forget again about all the parameters. It has this alpha 1, alpha 2 with some arbitrary phase, and once you plot it, it has enough parameter where you have this theta dm can be probed. For example, now this model can be probed through delta E, for the EDM in the future, at least most of the parameter space. Okay, at 2 loop. Now, can I for sure tell that 2 loop is not 0? I cannot, because I just found one diagram. There are many diagrams. One has to evaluate. Maybe they sum up to go to 0. I don't know. Okay, but here's a summary. So of my talk. So universal left right, the left right symmetry model can have a natural immediate spread cos left. Okay, left cross right. Open question neutron oscillation, absolute mass scale and mass hierarchy. It tells you, it gives an answer that lightest neutron mass is this. It is a normal hierarchy. There is no inverted hierarchy solution. Neutrinos, their own particle tells you it is the Dirac neutrinos. The answer is no. And Dirac neutrino by type 2 system mechanism. Is there CP violation? It gives a prediction on delta CP to be 130. Why is neutron mass so small? I will tell you it's so small because it is suppressed by intermediate scale over gut scale, which is already 10⁻⁷. The model solves strong CP problem. There is no need for an axion to solve strong CP problem. Theta bar is 0 at 3 level and one loop order. Okay, there is no double beta decay. And so if you don't see double beta decay in experiment, don't be surprised. Neutrinos are Dirac. Okay, and they suppress proton decay. Model can in principle accommodate Ahmed and variagenesis through Dirac representations. Dirac representations is a future work I'm currently brainstorming. Okay, with this, I'd like to advertise a conference that I'm organizing, BCB Spin, Particle Physics and Cosmic Himalayas in Nepal. I'm an organizer. Okay, if you'd like to come and give a talk, you're more than welcome. Thank you for your time. Yes.
So what would happen to the CK?
Very good. I have a better slide for that. Here. So of course I didn't go to all the details. So it turns out that we have three parameter this VR. Whenever you do a fit, you have a three parameter VR which is unspecified unitary matrix VR that you can choose so that the CKM becomes our.
And the CKM phase.
CKM, yeah, you can definitely do that. Remember that even though I am telling that it has to be the German has to be real, but the individual couplings are not real, right?
It's a little bit tricky to fit the phase.
Not in this one because no. Because the CKM is like you can whatever phase you require, it can come from this VR. And of course, there are other questions. I mean, I can ask whatever the RG is.
No, but that's okay. So just the question is there a correlation between your neutrino PMNS phase and the CKM?
I wish yes, but no. Yes.
So like I noticed like the scale of like mg was like very close to the m blank. So now the ratios of the mg over m blank that will be like 10⁻⁻⁴ish. So in that case, is it reasonable to say that the contributions from the Planck scale are like suppressed?
No. Very good. Now, this is a very good question. So he's basically asking, well, this M gut, it's anything. It's like a somewhat related quality problem. Okay. So this is the gut scale is so close to the Planck scale. Are there no operators that will spoil the strong CP problem? Planck induced operators. The answer is yes. There are Planck induced operators. Okay, which will spoil the strong CP problem because I can just write those terms. Of course, the coefficient doesn't have to be real, so you can't spoil the strong CP problem. Yes, you're right. So we put it under the rug, but it is much better than action quality problem because action quality problem is of course the quality problem is 10⁻⁴ something. Here is like maybe 10⁻⁷. Yeah. There is that. I mean, we try to, for example, I try to make the cut scale lower than the 15, for example. It would be slightly better, but I could not do it because it's quite complicated. But very good question. Yes. In fact, I wrote a paper recently. Using that one, I made it because I can use the same operator to generate. Again, I'm talking about Dirac neutrinos, but I can use the same operator to generate modular neutrinos. Now then I have a pseudo Dirac neutrinos. Okay, and then I ask question, well, if I have pseudo Dirac neutrinos by introducing this Planck suppressed operator, can I still solve strong CP problem? All the features that I have mentioned. And the answer is yes, and I will repeat on that again. Any other questions? And please do come. I know it's far, Nepal. It's very beautiful. Please do come.
Actually, I got a note from.
Yeah. I asked him to send you an invitation as well. If you want to give a plenary talk as well, just let me know. You'll have to come.
Anil?
So you can get trip to the Everest.
You can take a trip. You can take. I mean, it's quite far. You can take a plane trip to you just fly and then make a start.
See the long queue waiting to go on.
Twenty average is not easy. You have to walk a lot and. But there are.
You'll be there,
I'll be there.
Let's send the speaker again.
Nice job.
Thank you, thank you. You'll be